Today we are going to learn about mastering hyperparameter tuning in Scikit-learn decision trees. We'll explore how to optimize decision tree models using hyperparameter tuning, enhancing accuracy and efficiency. Decision trees are a fundamental component of machine learning, offering a straightforward approach to classification and regression tasks. Hyperparameters in decision trees, such as max_depth and min_samples_split, govern the flexibility and complexity of the model. These parameters are not learned from the data. Instead, they need to be set before training. The process of tuning these hyperparameters is crucial because it can significantly affect the model's performance. Scikit-learn, a popular machine learning library in Python, provides robust tools for decision tree implementation and hyperparameter tuning, making it accessible even for beginners. Hyperparameter tuning is a critical step in the machine learning pipeline as it directly impacts the model's performance and efficiency. Without proper tuning, models may suffer from underfitting or overfitting. Underfitting occurs when a model is too simple to capture the underlying patterns in the data, while overfitting happens when a model is so complex that it captures noise as well as the signal. By adjusting hyperparameters, we aim to find a balance between bias and variance, thereby improving the model's ability to generalize to unseen data. This process not only enhances model accuracy but also ensures efficient computation, which is vital in real-world applications where resources are limited.
The max_depth hyperparameter in decision trees determines the maximum depth of the tree. This parameter plays a pivotal role in controlling the complexity of the model. A deeper tree can capture more complex patterns but is also more prone to overfitting. In contrast, a shallow tree might underfit the data. In Scikit-learn, max_depth can be set as an integer, indicating the maximum number of levels allowed in each tree. To tune this parameter effectively, one should start with a small value and gradually increase it, monitoring the impact on training and validation performance. This approach helps in finding the optimal depth that offers a good trade-off between bias and variance.
The min_samples_split hyperparameter defines the minimum number of samples required to split an internal node in a decision tree. It governs the branching behavior of the tree, affecting its depth and complexity. A smaller value allows the tree to grow deeper, potentially capturing more details but increasing the risk of overfitting. Conversely, a larger value makes the tree more conservative, which might lead to underfitting. In Scikit-learn, this parameter can be set as an integer or a fraction. When tuning min_samples_split, it's crucial to experiment with different values and observe their effects on the model's performance to achieve a balance that aligns with the data's characteristics.
Grid search is a powerful tool in Scikit-learn that automates the process of hyperparameter tuning by performing an exhaustive search over specified parameter values for an estimator. It incorporates cross-validation, ensuring that the performance metrics are robust and not biased by the training data. Setting up grid search involves defining a parameter grid, which is a dictionary specifying the hyperparameters and the range of values they can take. By fitting the model using grid search, it explores all possible combinations of the specified parameters, evaluating each one through cross-validation. This approach helps in identifying the optimal set of hyperparameters that maximize model performance while minimizing the risk of overfitting. Let's explore a practical example of tuning a decision tree using grid search. We'll start by selecting a dataset, such as the iris dataset available in Scikit-learn. First, we split the data into training and test sets. Then, we initialize a decision tree classifier with default parameters. Next, we define a parameter grid for max_depth and min_samples_split, specifying a range of values to explore. We then set up grid search with the decision tree, passing the parameter grid and cross-validation settings. After fitting the model, we analyze the results to identify the best parameters. Finally, we implement the tuned model on the test set, evaluating its performance to ensure that the tuning process has effectively improved accuracy and efficiency. Once the hyperparameters have been tuned, it's essential to evaluate the model's performance to ensure that the tuning process has yielded improvements. Common metrics for performance assessment include accuracy, precision, recall, and F1 score, especially for classification tasks. It's important to compare the tuned model's performance against the baseline model, which is typically the initial model with default hyperparameters. This comparison helps in quantifying the gains achieved through tuning. Additionally, it's crucial to check for signs of overfitting by comparing training and validation performance. If the tuned model exhibits significant improvements and maintains a balance between training and validation metrics, it can be finalized for deployment or further analysis.
In the quest for the best model, it's easy to fall into common pitfalls during hyperparameter tuning. One major issue is overfitting, which can occur if the model is excessively tuned to the training data. This can be avoided by using cross-validation to ensure that performance improvements are genuine and not artifacts of the training data. Another pitfall is ignoring cross-validation altogether, which can lead to misleading performance metrics. It's also important to interpret the results correctly, considering multiple metrics rather than relying on a single one. This approach provides a more holistic view of the model's performance. By being aware of these pitfalls and adopting a careful, methodical approach, one can avoid these common errors and achieve more reliable results.
Efficient hyperparameter tuning is both an art and a science, requiring a balanced approach. Begin with a simple model and gradually increase its complexity as needed. This strategy allows for easier identification of when the model starts to overfit. Leveraging domain knowledge can provide insights into which parameters might be most influential for a given problem, guiding the tuning process. It's also beneficial to adopt an iterative approach to tuning. Start with broader parameter ranges and narrow them down based on performance observations. Continuous monitoring of performance is crucial to identify when the model achieves optimal performance, preventing unnecessary computations and ensuring timely adjustments. In conclusion, mastering hyperparameter tuning in Scikit-learn decision trees is a vital skill that enhances model accuracy and efficiency. We've explored the importance of tuning, delved into key hyperparameters like max_depth and min_samples_split, and demonstrated the use of grid search for optimization. Understanding of the potential pitfalls and adhering to best practices ensures a robust tuning process. I encourage you to apply these techniques in your projects, continuously learning and refining your approach. As you gain experience, you'll find that effective hyperparameter tuning can significantly improve your machine learning models, making them more reliable and efficient. Thank you for watching, and happy tuning!